Hello, this is Richard Collins with the Internet Foundation, and I'm going through the nuclear data on the Internet, trying to look at all the organizations and schools and users of the information. So, normally, a group goes and says, well, let's get everybody together, and so what they do is they go get the people they know who are working on stuff, and then they say, well, that's our group. But uh, there are gradations of these on the internet and in the world, and there's going to be for like nuclear data, all of the nuclear physics and introduction to nuclear physics kinds of chapters in every college and university in the world, of which there's roughly about 25,000 universities and colleges. Now, I learned some of this stuff in high school, and so I know, and there were people, if you go and look at, uh, it's been a while because we've changed a little bit, but it used to be that it was a good a good thing to do would be to become a nuclear engineer. So, uh, at least when I was younger. So anyway, let me take a look at this. All right. Let me just right-click and open in a new tab. All right. So here's one, and this is isotopic abundance and atomic weights. Okay. So, and this is formatted for humans. What I mean is a human has to read this in order to get it out. Now, I can write a parser to go in there. I can write a computer program to read this table, but it's in HTML. Let me look underneath. So this view the page source. Yeah. So this is what the actual page looks like, and then you see the table and such in here. So it's kind of a mess to get it that way. So this is called mining, like on the internet. You're trying to get and this only has the main, this has the average of the isotopes. So this is the standard atomic weight used if you're going like doing chemistry with no separation or anything else. So it's not very useful. So okay, so I'm just going to set that aside. Isotopic abundances, let's look at that one. PDF, kiss of death. I'll just be as mean as I can. PDF is the worst thing to happen to the internet. I know why Adobe wanted a monopoly on print format on the internet. I know how much they milked it, and it's bad for the whole world. Okay, now it's not unfixable, but it's a mess right now. What I'm talking about? It means that you come in here, you probably won't be able to extract the data out of it here. You won't be able to use. This is not a table of data. This is text. Let's see. Yes, I can highlight it. Let me see what happens if you try to copy it. It won't even highlight. I'm trying. Okay. So what I'm saying is, once you have it in PDF, it's almost always impossible to get back out. Also, the bad habit that most organizations have, they treat it as a print publication, and they use word processing methods. They assign the generation of this table to a secretary or a clerk or somebody, and they have to manually type it in and line up the columns and get things straight so that it prints properly. Well, you can't do any data work with that. Okay, so what you need are real numbers, separated, clearly identified, all the decimals, every line labeled. And then I'm looking here. Here's this got carried on. They say, well, for a human, you don't want to see repetition. Well, for a computer or anybody doing any kind of study, you need every line to be well labeled. So here they didn't bother to continue every line. So that got carried on. So this this is PDF, and that's not going to be very useful. Okay, so I'm just going through what I normally have to do. I see massive value. Let's take a look at that. What is this go? I'm just looking at the PDF again. So, oh, and can I even have access to this? A lot of these, let's see if they'll let me. Okay, so I went to PDF. Oh, and then I have to log in or pay. Okay, so I think that the federal government, the U.S. federal government, should not be in the business of sending people to for pay things. If you're going to share, then share it. And if you're going to refer to, if you use this information, the only way I can verify it is to be able to go back and look at it. So for verification purposes, you need to have an accessible copy of that. Now, I know there's always issues. Everybody wants their money. Everybody wants their piece. Okay, so I'm not going to do this item by item. That'll be a mess. The HTML table I happened on there. Let's just take a look. Oh, okay. So, and it did all. So this is the same thing. And underneath again, this is what you're working with. That page that we're looking at, this is actually what it looks like. Okay, so you can't take this page as it is. If I tried copying that, and here's what happened. Okay, so I copied this HTML here. That's just this side here, and it's a mess. Okay. One of the things is that for human readers, they put spaces in here, so I can't really use those. So the HTML does come in. Now, jumping ahead here a little bit, let's go back to this one. I did all isotopes. The linearized, well, this was somebody's idea about, well, this is sort of, let's label everything. And this is sort of an XML JSON type of thinking. Oh, I'll just put a label on it, and then each item is there, but it needs to be in a record. Okay, so you really need that. So that's not a good way. If you're going to do this sort of thing, then just go ahead and stick it in JSON, JSON, which is the JavaScript exchange format. It's not pretty, but you can do it, and then most JavaScripts can read. The safest and easiest and fastest and most universal method on the internet that I recommend as the director of the Internet Foundation is to use tab-separated line feed terminated lines records. Okay, the reason for using control characters, tab and line feed, is they're outside the ASCII data set, and that's what their original intent was. You transmit a packet of information, the character sets that you're transmitting and the control characters are two completely separate and identifiable things. If you go in and do a lot of the XML and stuff, I was looking at the U.S. financial data, for the government agencies, and it was all in XML. And the problem was that they did XML with quotes, and then they had to backslash them and double quote them, and just every single transformation added so it was about 100 times as large as it ought to be. So the data was only 1/100th of the packaging that you had to do, and that's kind of what's going on here. This could be a very compact listing, but you look at all the characters there and all the work that you have to do to get this in where you can work with all of the numbers at once. Okay. And we need to work, the whole human species needs, and actually all the people on doing nuclear data of any kind, they need to be using these as a whole and all interconnected and all cross-checked and verified. Okay, let me close that. So this one, no. Let's go back and, let's see, I've got to find my way around here again. So how did I get here? You can't go back. Okay, this is a bad page. Okay, It says standalone. Okay, so it got generated here, and let's see. Can I go here? No, I got it. It's findable from the internet. Okay, so this is an entry page for the internet, and that's actually where I started. And then the problem was, you have to go. How do you get back above? What's the context for this? Who's the owner of this page? So every website on the internet, every gov page, or every page on the entire internet has the same problem. And so let's say atomic weight. Okay, so this gets back to here, but it needs to be at the top, and it needs to be easier than that. Okay, let's go. All right, so back here, and finally, I'm going to try this version, all isotopes. And this is one. Now, this is, again, this needs to be in a text. It's a HTML wrapper for text. Let's look at the page source. Okay, so this is HTML, so it's a file with HTML in it. So I can't just say right-click and save, because it saves it as an HTML file. What you need is a download as a ASCII text file, a tab-separated file. Let me see if I can make one. Okay, how do we do that? All right, so here's a text file. This is the text portion of it. So what I did was I highlighted it carefully. Okay, I'm holding the Shift key down now. And I'll go to the bottom, get that, Control C. All right, now, let's see if I can do that. All right, I'll leave this and throw it away in a minute. Okay, I'm working on all the data at once. You can put them in one spreadsheet. All right, so Control V gave me a fairly clean thing. Let's see if we can do this. Now, it's not apparent in here because they're using a proportional font, but this should be a fixed width. Let's try this next. Okay, this is hard. It's got to be there. That's extra. This seems okay. It's not going to, I won't be able to do this in one cut. Okay, let's see. And you have to, basically, I have to, in this box here, I have to scan down ahead and try to, well, let's see if we can do it. Okay, so I managed to get that. Now, I've done this. Oh, an isotope got cut. Okay, so let's insert thing and index. I think I better, I think I'm there. Q zoom. Let's make this. Okay, I'll make it a little bit easier. Okay. All right, what I'm doing is putting an index on this first thing. When you get a raw file like this from somewhere, if you're going to have to sort it for any reason, you don't want to lose the original order. I'm going to be deleting extra lines that I don't need. That's the first thing. Okay, so we got down to here. This is always so tedious. This is, if I have to do this, and I'm really fast at this, right? Okay, I've done this all my life, just about. Okay, so I need to, this is going to get in the way. Let's see, this is 1, 2, 3. There's a, oh, this is in. This is oh, that's my index. This is Z. Okay, symbol. Okay. All right, let's see if we can do the, oh, atomic mass. Composition, we'll have to sort that out. Atomic weight, notes. Okay, so this is kind of, let's just see if we can get this cleaned up a little bit. All right, so this column, this is the good stuff over here. So let's see if we can do data sort. Okay, so it is, my data has headers, and okay, cancel. It's not going to let me. Let's delete that thing here. So it didn't. Okay. Data sort. My data has headers, and I'm going to sort by atomic mass, and it's going to make a mess. I don't care. Okay, sort. Okay, let's get rid of these guys. Okay. Right click, delete. Okay, so let's look at the bottom. Okay, so that's fairly clean. We're getting a little closer. Here, I've got the thing already set to sort, but I'm going to be really conservative and go this way. So make sure there. So I'll sort it by the index there. So now it's back in the original order. So Z, I'm going to have this. I have to copy it. If I drag it, anyway. So there. Okay. 2 Control C, V, Control C, V. I only have to do this 100 times or so more. Anyway, so okay. Control C. Oh. Control C. Now, there is value in doing this, and I'll tell you why. Because when you get all the stuff into an actual database, into a form like this, where where each line can be moved around separately, where you can sort it and filter it, then you can basically track everything. Control Z. Let's get there. Control C. Now, you may not want to watch me do this, but imagine I don't know, I estimated in the other video that I just made yesterday, I think it was, there's about 50,000 people in the world who probably are going to be learning nuclear physics, okay, nuclear engineering. If I'm right, and because I see so many new things that are starting out there, then there'll be an explosion in nuclear, and actually I call it atomic things. And what I'm talking about is all of everything in the energy material, basically materials and energy storage, chemistry, nuclear atomic chemistry, from 10 electron volts per bond up to up to basically 10 MeV per bond. Now, I went a little far there. Okay, normally people say, well, 2 MeV per bond is nuclear, and that's the kind of thing. But because all the small ones vary, basically, I'll do. Anyway, I'm still cutting it. I don't actually. I store most everything as pictures. Okay, so the only way I can do these sorts of things is if you don't use words very much. The reason is words are useless if you're going to also have to deal with translating to different human languages. In just the computer language versions of these things, there are hundreds of there. Now, there are some major dialects, okay, so if you go in and, you find the people who only speak Fortran, well, there are actually many dialects of Fortran, and there are many communities on the internet, all pretty much isolated and not interacting, okay, and the reason is they can't talk to each other. When I was growing up, a lot of the dialects in the United States were so separate you couldn't understand them. Part of that was, I realized in retrospect, it was I was young and I didn't have any exposure to all those different ways of speaking, and so somebody from another state. I live in Texas, so there were Texans you couldn't understand. So anyway, with public broadcasting, the news and the Edward R. Murrow and those sorts of things, pretty much the human English language kind of made it. But we're in the state now that all the scientific and engineering languages are not interconvertible. They are interconvertible. It's just that people don't do it. Okay, and it's hard. Okay, I've spent my entire life learning and memorizing things. And the problem, even now, it's worse, is because the cycling time, people will come up with new ways of talking, and you get a fad, and everybody will start using a different language. Okay, the quantum stuff is like that. Okay, everybody's young and excited, and everything is quantum, everything is AI, everything is that. There's nothing wrong with having enthusiasm and doing it. The problem is if you don't build bridges to the older stuff, then ultimately somebody has to clean it up. And I find whole regions of the internet, like I say, that are completely independent, yet they're identical. Okay, so I someday I'll make another video here. So. Okay, so there could be. I mean, the time it takes me to write a program, I'll tell you this: hard lessons. If I tried to go in here and write a little program to do this, if I had it set up and I was doing it every day, this particular kind of thing, then it wouldn't be so bad. But if you have to go in and say, well, what form can I get this into? There. You can't do it. So why? There. All right. Let's see if I can keep going here. I think I only have a few thousand of these to do. A few thousand total of it. Now, I still have to split the other column. Luckily, there's at least a parentheses. It's not horrific. There. But. Last year, and still I'm working on COVID. Internet. It's one of the internet is one of the major problems for why COVID isn't solved yet. Okay, it should have been tracked from day one, and it should never have gotten that bad. I know why it didn't. I can see it on the internet. I can trace it all facets of that. And the research for it is almost all PDF. Okay, the publishers, everybody in the whole industry puts it on paper form, either literally on paper, or they stick it in PDF or HTML. Oops, Control Z, Control C. Pardon me, I'm talking and not being careful here. Okay, so I've traced that out. I've got a project going to try to get all the PDF changed over to where you can extract the data, the tables, the numbers, the dates, the people, the places, the references, pretty much, the guys who do mining and classification, human language processing have to deal with this. Google has to deal with it. Everybody who goes out and wants to index the internet gets to, well, what in the heck is this? And it's in all these different formats. The symbologies, fonts, codes, and things. It's not impossible to fix it. Look what I'm having to do here. But this is such a high value, if you like, or high value to the human species data set, because you can't do any of the others. I was doing it. Let's see these other ones here. So I was looking at these are half-lives from nuclear NUDAT 2, I think is where it came from. Okay, so where's my sheet? I'm here. Okay, so I'm going through those, and you can't resolve them unless you have the masses. Okay, so I had it. Stone. Okay, I'm pretty sure it was Stone. I've read the CRC handbook cover to cover many times, and the part that gets the most thumbed is the table of the isotopes. And the reason I use it a lot is because it has, I learned magnetic resonance imaging, actually. That's where I started on magnetic resonance was the imaging side of it. And I wanted to generalize it and use it for all elements. And to do that, you have to go in and find the magnetic moments of things and the quadrupole moments of things. And the only place that I found them was in the CRC handbook and the table of the isotopes. But because I read everything, I also, when I would remember the magnetic moments of things, I would also see the isotopic masses and the beta decays and the rest of the things that are in there. So it's there. It's unfortunate that the CRC handbook is not a database, not an interactive tool, not a database where you can actually do calculations and estimates and hypotheses and say, I was going through this. I actually started here, not that one. I was going through here. I was basically, I had the SPs, the separation energies for protons and the separation energies for neutrons, and then I took these from CODATA and a couple of other sources, and I was basically re-engineering. So you can work backwards, and I'm going to do that. I think that was my intent here, is to go in and correct it. Notice where I'm at now. These are in KeV, so drop it down by 3. So I'm basically in micro electron volts, and for the things that are happening on the internet, the level of precision is moving to the point where at some point people will be working at nanovolt resolutions, nano electron volt resolutions. That's my nominal goal for nuclear data, is that it should be there. Why? Because nuclear fission reactors are sensitive to gravitational potential changes, to gravitational acceleration changes. And so you can monitor the neutron statistics if you do carefully, and you can see the change because of the sun and moon over time. Anyway, that's just so there. Sorry, here. Let me get back to. I got a little bored copying these. Okay, let's see if Control C. I forgot what PM stands for. PM. Actually, I forgot what samarium, right? Control B. PM. What the heck? Oh, maybe I'll go look at. Oh, yeah. Some stuff, my older stuff, is starting to fade a little bit. I can look, and I first read the table of the elements or something back when I was in grade school. So the human mind can store a lot. I think I've tested it about as far as you can go, trying to read and memorize everything on the internet. You have to, okay? The speed of search and resolution, say you're reading a paper on quantum statistics or something like that, okay? Well, the terms in there are horrific, okay? And they're context sensitive, so there's terms that only a small group will be using, maybe 4,000 or 5,000 people, and they're using one set of terms. And there'll be another group, and usually in a competing school or community, and then they'll be saying something else. I'm going to hit the save button. I just realized that if there's anything that can go wrong with the computer, it's happened to me at one time or another. I've lost whole things. I've lost computers and disk drives and work. Oh, you spend a few hours on something and then bang, you lose everything. So, okay. Now, part of why I'm doing this, okay, I'm deliberately showing you the tedium of what they're. Now, okay, let me explain. Okay, all right. A human's reading your table, right? And they're looking at a section of that where they've got LU and that, and then they've got these long empty spaces in here. They'll come to a number like this, and they'll have to basically mentally transcribe these two things down to here. Do you get what I'm saying? You can't look at a human looking at this table. When they look at this, they have to resolve it. I've gone through the human side of the perceptual side of data on the internet. It's one of the parts you have to deal with, because how many eyeball screen feet are you requiring of a person when they come to your page, right? Okay, you open up a page, any page on the internet, and if it takes them, if their eye has to traverse 2 inches of screen to get what they're, or if it has to do 20 inches of screen, those are totally different. You get what I'm saying? Tungsten. I saw some really weird things on tungsten earlier today. See. Yeah. All right. So we're almost there, I think. Should I have pity on you? What I want you to understand is that if a human's going to be reading this, you really need to make it as clear as possible. And no human, especially I'm talking about those kids. There's about 2 billion kids in the world, what I call first-time learners, from 5 to 21, 22, somewhere in there, in the world. So and there are many of them. I figured about at least 50,000 of them. Probably that's 1 in 10,000 of them will of the older ones will go in and go into nuclear engineering. Nuclear engineering. Now, I have sort of a private bet with myself that a lot of those people won't go in there, that actually it won't be called nuclear engineering. What it'll be called is gravitational engineering. Okay? And the reason is the requirements for gravitational engineering are so much more stringent than anything anybody in nuclear physics does, that's where the money's going to be. Okay? So you learn difficult things, you get paid more. Okay, it's just the way of the world. Okay, I think I'm getting a little bit closer. Okay, there. So I think I'm going to have. I've done this every 10 years all my life. So at least 5 times I've gone through and done the whole study of this. Okay, so I calculate the binding energies. I look at the current structural models for the nuclear. Let's see, when was it? Let's see, I worked for Detroit Edison. Okay, that was in 1975 or so. And so I went through there. Let's see. And then when I was working at Phillips Petroleum, that was 1988 to 90 or so, in that range. I had to review Pons-Fleischmann and fusion and some of the other things. And so, again, I had to do it. Okay. Went to Georgetown. That was in the early 80s. I was taking chemistry while I was working at the Center for Population Research, and I took nuclear and so I had to do it then. Oh, and also when I was all the times, every time I keep going back to magnetic resonance, it's a nuclear magnetic resonance. Okay, so the the vast bulk of the things are their electron spin resonance, and then all of the positron and everything else, and muons and all the other stuff. It's quite a particle zoo, as they used to call it. So you can get the you have to think about the nuclear structure at the same time you look at the nuclear magnetic moments. Now, the first day I took chemistry as a freshman. My older sister was in the class, and that was in Galley, Florida, pardon me, and that was we're at Cape Canaveral, or that's where my dad was working, and the teachers were from that group, and so we got a pretty hefty senior chemistry for me as a freshman. I kind of struggled with it because I hadn't had algebra yet. That kick-started me and said, you better go and learn math a lot faster and better. So I kind of did a little bit of catch-up, and then eventually I did really well. I don't have many things that I do where I get like prizes and things. I just don't go that way. But I got a perfect score on my SAT in chemistry. I was so proud. I was so proud. Then I went to Case Western Reserve, right? Okay, I got a nice full scholarship there, and I was so proud of myself. And I went in and I mentioned, I got an 800 in chemistry and SAT to my roommate, right? He says rather casually, well, I got an 800 in math and what was it? It's math and I forget the other one right now. Boy, I'm really tired. Okay, and then on all of his special subjects, so he did like physics and things. I don't think he did chemistry, so I had a little bit of a reprieve there, a little bit of my humility, a little bit of my pride intact. So, yeah, that one instance there, that changed my entire life. I said, never say anything prideful about something you've done like that. So anyway, but if they had asked more questions on the SAT test, I would have answered them. But it told me that I did it deliberately. I just simply went and memorized every question, every possible thing that was there. If you can memorize things, you can get good grades. Okay, that's all they're asking here. Just remember the answers to these questions and all. They won't let you read the book, but if you memorize the book, you're okay. Okay? So the people who have good memories tend to do well. You can learn that. You can practice it. You can get better at it. You can think. Oh, in reading these things. So I read. I probably anywhere up to 1,000 papers a month in there. Something UUP. I don't know what that's going on. Something here. So this goes down to here. That has a name. Okay, so this one, Control C. That's going to be a note. I'm pretty sure I'll leave that as a note. do the same here. There. But when you're reading, you have to resolve things. If you had to go look it up and search every single term in a paper as you're going, you don't do it. So the first time I see a new term, I do look it up, or figure it out from first principles, and then memorize it. And there. Now I'd like to get the computer. Okay, these are sort of messy. Okay, let's see if I can get this. Okay, so there's stuff in that column, but I need this. Okay, so I'm going to insert a column here to save, because I've done a lot of things. So the extra column is this way. So I go down to here. Did I get them? Yeah, okay, got them all. I'm going to do a split on this by that by parentheses, so it'll get that column into a separate one. Finish, and then I'll take this column and remove the pound and the parentheses. Let's see if I can do that in one. So I do that by here. So let's just do pound parentheses. We'll do the big one first, and I'm replacing it with nothing. So there, and then, okay, and then parentheses, replace it with that, replace it. Okay, so close that. So and this now, I don't know, I guess it's parts per million. I have no idea what exactly the thing is there. It looks like, 96 parts. Yeah, that needs to be done in a proper form. I don't think the way it's like here. Let me look at a couple of the 70. Is it 7? It's probably 70 parts per million. Okay, let's insert another one there. This is parts per million, I'll say, even if it's not right. Shift end home gets me down here, and now I want to go through and split that by parentheses, and then here and home. Oops, wrong one. I hit the wrong. End home. I'm holding the shift key down, back, and then in here remove that parentheses, replace that. Okay, close. Oh, and I might have missed something here. Let's see if they left some pound signs in there. Oh, that pound might, you know what that pound might have been? No, I don't know. So, all right, so standard, atomic weight. Oh, brother, what a mess. Okay, they use square brackets in here. Maybe that means something to somebody. And these compositions, okay, those are only a few of these. These are the stable ones that have numbers on them. Okay, I'm going to leave that for now. I'm not going to try to. I got my basic table though, so I can at least use that. The symbols are, in a sense, extra. Okay, so I'm going to move that over there. And then my index is in the correct order, and I'll just delete that as a thing. Okay, so I could leave it there. Sometimes if I had a perfect system, I would have a system that never forgot, where it had an infinite undo. You almost have it in here, but it's not in an auditable form. So, like for instance, if the undo transaction list for Excel were available, if it were auditable, if it were recorded, then you would keep a record of all the transactions. I worked as a chief accountant for a Texas Education Agency. They helped set up they had an RFP for their central accounting system. And what I did was to audit all the methods, the human methods. I walked table and desk to desk and tracked all of the forms and data flows and human procedures. But because I had the computer experience, I audited the internals of it and then somewhat the software and the specification. So you have to have all financial and accounting systems on the planet need to be audited, both the human side and the computer side. And if you don't, if it's a black box, basically you get a chance for people to manipulate or do illegal things with it, or just do stupid things, pardon me, but that's the way it happened. When I worked for Georgetown University, I spent 3 years at USAID setting up their central economic and social database. So all the international and federal agency databases on countries and everything about countries. There's about 27,000 variables in there. And I put those into one database, not a dozen that were all eclectic and different language and different styles. So I put them there. So I do have experience doing that. I was already good at it when I was doing that. So it's part of the way my mind works, that I can see, I can see many different things, see how they all fit together, put them in there, clean it up, do it, and then get it into a functioning system. So but the International Monetary Fund and the accounts for all the countries were that way. But I was also looking at the federal agencies because I was doing budgets and things, and so I looked at the chart of accounts, basically the accounts and for the U.S. government, all the things. So because in D.C., if you're inside the Beltway, you have to know about federal accounting and contracting and those sorts of things. I eventually worked as a contracts manager, Federal Transit Administration, things like magnetic levitation and all. But I looked at their whole portfolio of things, and I could see that they really needed a better central system. Okay, so pardon me. Okay, so I got my table. And then I skipped a few here. I was doing just the numbers at the beginning, so these get carried along. So I didn't miss many, and then I started waking up. Okay, and then these are all hydrogens, yes, down to here. So, and then here, I'm going to do this in comma format, and these are atomic mass units. So really, when I put this into electron volts, it's going to get really long. So probably what I'll do is shift all these tables to scientific notation. Unfortunately, in Excel, scientific notation chops off there. It's not a infinite precision thing, so it rounds. I was talking to my brother yesterday about the rounding errors, floating point rounding errors in a lot of software, and it's a common problem. If you're doing precise work, I did satellite orbit determination, and the you can't miss there. I learned, even then, 16 decimals was hardly enough if you want to restart a very large calculation. So I use the solar system ephemeris a lot still. So I've continued that. That's been 50 years or so since I learned how to do orbit to do orbit determination. Those things are quite precise. And now I'm to the level I can get the data in to correct the Jet Propulsion Labs stuff. Okay, because I can check the gravity directly. That's something else. Okay, all right. So I got that in here. These are fine. This is my atomic masses, and these are just, I'll just say masses, because they're actually isotopic. They shouldn't be called atomic in here. These are isotopic masses. And I need to get them all. These are atomic mass units. There's, I think, I don't know. I'm going to have to check in here. I think there's a lot of stuff where people like left things out. Now, I haven't checked all the different research in here. It looked pretty varied in there. If you look at the experiments on all of the stuff that this came from has been done again 5,000 times. Okay, like let's see if I can do it. Okay, like so save that. I want, because I'm going to come back here. Let's see, tritium mass. Okay, let's just look at that. Okay, so 3 mass 3. That's where it's written right next to each other. So there were about 9,000. Let's get this back to. I had it blown up for some reason. I hope you can read it. Okay, so tritium mass. Okay. About 2.3 million, and that's more of the working level in the world for groups and people who use that fairly routinely. Okay, now if you just did tritium, you get everybody in the world who's just mentioning it because it's a cute name, right? Or tritium jewelry, or tritium golf course or something. Somebody uses it for other reason. But if you put mass in there, you can narrow it down. I've become quite good at slicing and dicing the internet. I've been 7 days a week, 12 to 18 hours a day, 23 years, do the numbers. And sometimes I work more than that, but generally the average, at least the bare minimum is 10 hours a day, 7 days a week. So anyway, so some of these things, I mean, here's stuff going on. Okay, so here's isotopes of hydrogen, and how many people come and read Wikipedia? Well, a lot. How many come read the Isotopes of Hydrogen page on Wikipedia? I don't think they have that information in here. They might. It really ought to be. If it's a public, global effort, then the activity on there is important. These are horrible pages. And why? Because these things here are not identified as isotopes as isotopes. Okay, they need to be called, that symbol needs to be called isotope in some sense. Deuterium needs to be identified there. And here, even though it says isotopes, you can't go in and do it. So I'm trying to get, I like that Wikipedia went and put in what called hover boxes. This is a concept I'd like the whole internet to use, but a lot further and deeper. The reason what I'm complaining about with them is they made their own purpose-built, human have to do it, blob here. Okay, they basically did a sort of an abstract and an advertisement for the pages, and they and it's not a preview of the page. It's something they did. So that's a lot of extra work. Okay, and it has the potential. Generally, it does give you alternative information. It's not a precise and complete preview of this. Okay, and you can't go any deeper. If there were links on the preview, if it actually previewed the page instead, then you would basically go in and you could do it. In which case, my requirement for a hover box is that it be movable. This one is not. Minimizable, savable, and all. So what you would be doing is looking at a window to the new page. The thing that's killing the internet, a huge waste of time on the internet. It's in the probably up in the trillions of hours, cumulatively. Let's see, per year, easily billions of human hours, maybe longer. Here's what's going on. To get this one here, the hover's nice. You get a little hint about there, and maybe you don't even have to go. But most of the place is you have to open a whole new page. If I were sitting here, most people just click it and they go to a whole new page. Their mind has to remember the connections and maintain the context, and so they lose it. So you have to either physically go back and do it. Now you think, well, that's not, it's so easy, you just click back. But it takes seconds, and it takes computer resources to do that. And and all in all, it's not a good thing for the internet. Particularly, a lot of times when I go through here, partly because I have memorized all of the pieces of that, I don't need to go look at the neutron things, and I certainly don't need to look at a cutesy, diagram that doesn't tell me a ding about neutrons. Okay, it's just some cute logo somebody threw on there. That's what I don't like. It's wasting time. Okay, give people real data, real tools that you can do things with. Okay, so anyway, and then names. Well, that one's kind of cute, but the label's there. So anyway, so I have about 1 million. No, I don't actually have a few thousand core things that need to be done. So here's this table again, and these are just let's see, 1, 2, 3, 4. No, and see, they didn't go. This is just hydrogen. So Wikipedia didn't say, they don't have a central database of these constants. And I bet you, let's look. Okay, they stick a space in there too. I hate, on CoData, on NIST, they put a space in, and I have to take it out every single time. Now this one did it by logic. So let me look at this number here. Okay, so yes, if you go check, I do this often, I'll check actual constants, and if you put them in quotes, you can track them down. So I can track down every place that's using a constant, or a good many of them, on the internet. And I do that periodically. I can't do everything, I can't do all of them, but I do it as a process of, if you apply this method of searching on the internet, can you find all the people involved? And what I'm looking for are the people that are. Now you got flashcards, people, you need to memorize I memorized all the fundamental constants, that list of I think it's like 100, 200 things. I memorized those out to 6 or 8 decimal, as far as they would go when I was younger. I don't do that anymore. I still remember a few, but the computer can do that, and basically the hover on things, I should be able to hover that number and get the background on it. Okay, anywhere on the internet, if that number shows up and it's tied to a specific reference, then I should hover it and go back to there. So that's what I'm trying to get to for the internet. That's my concept of and vision for, let's get the internet connected. So if you say nuclear binding energies, you wouldn't do this. You would say you have a responsibility to show people depth. Okay, even in a 20-year-old Google layout that they haven't changed or upgraded or done anything with. I'd like to see them give me all 28,200. If you're going to say that, I want to see it. Prove it someday. Okay, show me all 28,200 of them in a table where I can actually work with it. Okay. Anyway, so this one, okay. Let's see. And so you'll see that they're quite specific. It doesn't work on everything. There are some ambiguous things, where something like a mathematical number and and a real value. But for the fundamental constants, it does work. Now, on things like speed of light, really basic things like speed of light. Okay, let me show you this site, Wikipedia org. 18,000. Okay, so the exact phrase, speed of light, occurs 18,700 times on Wikipedia. I presume, I'm hoping that Google's fairly reporting exactly what they have. I'd like it that if they would do more, but they don't. Okay, 2 point. Let's see. I am so tired again. If I did have a calculator, hang on a second. The 7, 9. My brain's so tired I can't remember the speed of light all the way. I'll just 2, 5, 8. Okay, let's see if I got it. Okay, 245 times. Okay, that exact value is mentioned in Wikipedia. Now, if they put it in a different form, in different units, if they did it in kilometers or something else. So what I'm trying to get to is that, in the kind of world that I'm looking at for the internet as a whole, that's my job. Okay, 23 years. I took over when the original Internet Foundation was canceled. I took over the domain, and I tried to take on the mantle of, and the responsibilities. What should the Internet Foundation do? So one person's a little funny to do that, but that's what I did. So I see that, all the national standards groups in there. Okay, let's see. So if this is site.org, let's see, site.gov. Well, that's pretty thin. LBL, NIST. Okay, maybe that's good that that you have so few, but every one of these, if LBL should not have their own, they should refer to the central constant, or they should hover it, right? So anywhere they have it, it's recognized as a universal constant and identified in every context. That puts either the browser or a community of people who make browser assistants can go in and do that. So people who do nuclear physics, I'd like to give them a toolkit so they have all of that and then in there. But you don't know who might be the next Einstein of nuclear physics. Then you have to give it to everybody. And so I'm trying to make it part of the browsing experience on the internet that everybody has access to the best tools for whatever area they're looking at. So if you go to nuclear physics, then all of it's laid out neatly. The parts are interchangeable, the things bolt together. The standards are one reference, and then all the associated groups. So yes, I know there. I measured the speed of gravity. That's one of the things I've done. Few experiments I could do was I used the superconducting gravimeter network that we had. This is about almost 20 years ago now. And I used it. I calibrated it as a whole network and then used it to measure and put bounds on the speed of light, speed of gravity. It turned out it's the same. Okay, that was my conclusion. And it was so hard to, because they were single axis devices, there was ambiguity in there. And I didn't have anybody to help me. So and I had a lot else to do, so I just set it aside. I did go through all the seismometers and check them, and you get the same result. So you can there's a few hundred broadband seismometers in the global seismometer network that can track the sun and the moon, and then because that's a straight linear regression for each axis, you can calibrate and do a speed of gravity experiment with the seismometer network. So anyway, so many things. I see almost everything. So there's so many things I'd love to do, but I don't have any way to get anybody to help me, or there. I'd love to see the gravitational GPS that I saw. A 3-axis MEMS gravimeter. Once it's calibrated, it works as a GPS, a gravitational GPS, and it works under the ocean. It works under the ground. It doesn't get distorted by the ionosphere. Okay. So, and it isn't blocked by conductors, right? So you don't have the problems of electromagnetic waves there. So I thought it was cool. I thought it was just elegant. Now I've mentioned it and tried to get people to say, "Oh, well, wouldn't it be? Here's this thing, gravitational GPS, works everywhere." No interest. No interest. Okay, well, what next? All right, so constants. Now, if I go to a NIST, okay, CCB, speed, let's just do speed of light. I'm going to go ahead and do this CODATA. I want to show people how bad this is. You go here, okay, these things, it's irritating as heck. Okay, that is for humans to look at, and they were so wonderful and all. They left the daggum thing. I think I spelled it. Okay, there. Okay, so see that every time I want to use any of the NIST-based fundamental physical constants, when I refer to them, I have to read them as a human, and I don't have an API. I don't have just a text table of these things there. And actually, I would say if there's okay, so sorry. Okay, so it searched. What happened there? I'm just curious. 838,000. Oh, okay. Well, that's interesting. I did that by accident. Before I was looking at that, 721,000 mentions out there. Okay. Now, I do these things. Now, let me show you something else. Okay, COVID. Oh, you do it up here. Okay. COVID. There it is. There. Okay. COVID is. This keeps coming up. Either they're lying, or there's a bug in there. It used to be for everything up until last week. It was 7 billion, right? And now all of a sudden, overnight, or within a few days, now it's 25 billion. Okay, so if I take that at face value, that says 25.27 billion entry points for that. If I do site gov, there are 227 million entries for that. So the whole world looking to the U.S. government, which is the federal and state and city and independent agencies that are under the gov domain, not a big domain, but it has 227 million mentions of these terms, and that means that how do you, what is there anything authoritative in there? There is no authoritative place on the internet for COVID, period. Watch this. Who.int. Okay, they're supposed to be the central place. They have 1.6 million entry. It's gotten worse. It was only in the 400,000 range, months ago. You know what I'm saying? That means that they're just plastering their site with mentions of this. There's no separate, they don't say, well, wash hands, wear a mask, about probably 40% of their things are probably wash hands, wear a mask. The other ones is closed or project or, announcement or event and things like that. So not knowing the context of the use of these things means that you really can't use any of that information. This compilation and understanding time is horrendous. Now I do it sort of professionally to go look at these things, But the real problem is that anybody who goes out there, just an ordinary citizen of the world who goes on the internet, there's about 4.8 billion of them, by the way. So that's the rough estimate of how many people have some access to the internet now. 4.8 billion people. So multiply 4.8 billion by people searching on who.int and trying to get an understanding of it. There are 1.66 million there. So 4.8 billion times 1.66 million. And that's the search space, the cross intersection of those two. It's not quite that bad, but for practical purposes, that's a good order of magnitude of the difficulty of the, that it introduces into the world. Now, even the people inside who.int in the UN system don't have a good comprehension of what who.int is doing. Okay? Just the departments that are directly responsible for are all over the place. They put things here, there, and everywhere. They don't put data as data. They're still using PDF. They handwrite their tables in PDF. So when they come out, you can't actually use them. So it throws a burden on anybody trying to do any kind of analysis and communication standards. The death rate in the world, there's a few people who have collected by age and sex. Let's see, Max Planck Institute. They have a group there. My memory's gotten bad for some reason. So anyway, fundamental constant. Google distinguishes them. Okay, you would think if you don't put quotes on it, fundamental constant. They're actually totally different things. When you do the plural of something, you're looking at the whole of it. Okay. 478,000 now. Pretty much in most of the physics and engineering and science teaching in the schools, they generally don't really get very deep into fundamental constants. And that standard model, if you go look at the standard model, it's not quantitative, it's a concept. Okay. There are a few people who go in and actually work with the models and the relationships between the constants. They're implicit back in here, and this thing here, correlation coefficient. Let's see, there. Browse complete constant list. Oh, brother. Okay, so alpha particle map. Okay, so they do, this could be improved quite a bit, but anybody who's going to ask these questions wants to work with the whole list. You want to say, show me all the correlations with all of them. Don't screw around and make me pick one, and then you show me stuff that only a human can read. So it's in a pretty text. It's not in you can't, even these uncertainties are, those are just pictures. They're not numbers at all. They're not even easily converted into numbers, okay? Unless you write a program to do it. So anyway, this thing here is good. Let's see, alphabetical list. Where's the list? I click. I don't want to look at a category. I want to see all of them. Table. That's an image as a table. PDF is image. So this is totally useless for numbers, okay? Because you have to read, a human reads it, copy and paste. Probably sometimes, a lot of times, just manually transcribe. Same thing. If it's in an image, you have to manually transcribe. An alphabetical list here, but then you squeeze them down and give them in piece by piece. Is it give me the complete list? So anyway, these things, they used to have them. Yes, they do have there, but there's no units. You can't actually like pull the equation out and save it and work with it. If you took all of those equations as relationships, you can begin to like map and walk through the entirety of this as a whole, not as memorizing each pair. Okay, right now, if you take 1,000 things and do, well, I don't think there's 1,000 or 200, and you take them pairwise, that's 200 times 199 over 2, 19,900 things that you have to look at. But if you take the set of equations, that's a much smaller set, and then let the computer take care of it. Okay, and you can browse and look and find connections and things. Some things are not connected at all. Other things are, and people argue and talk paper for years on some of this when it's all there, and it could just be a live, living model of something. So what I'm trying to do, I'm talking about in a tiny little way with just a few numbers, special symbols and unique character strings in here. Okay, is the Planck length used anywhere? Let's see. I bet it is. Let's see. So you don't need all of it. You can go in and okay. So it does have. You can find groups that way. I've actually done in a few cases like terahertz or THz, like that. You can actually get a pretty good handle on communities by the units they use, and I do that all the time. It's actually one of the best slicing, dicing methods you can use on the internet if you're trying to get to technologies and things. And I use it all the time because when you cross those things with then you get to some of the cutting edge work that's going on. The processors are fast enough. You can do time of flight on anything. I'm trying to get time of flight into gravity. I should stay absolutely neutral, but I have a private interest in gravitational detectors. That's where I went to school and learned that, and I wanted to be in that community having fun and all. But so anyway, the time of flight, if you can. If you have a 3-axis detector and it can do time of flight, basically what is it? You're doing megasamples per second. It's pretty crude, but it works. Or gigasamples is what I'm trying to get everything to. Then you can know from what direction and quite precisely there. If you get an array of these things, you can basically, just like radar, you use gravity and you just say, where did it come from? It comes at exactly the speed of light, and there. So the earthquakes, the Japan earthquake registered on the superconducting gravimeter network, and it registered on the broadband seismometer network as a gravitational signal coming at the speed of light from the spreading seismic wave. It isn't like the energy at the point did it. There might be some noise from there, but most of it is the rather large signal that comes from the seismic wave. It's so big, the LIGO has to shut down when there's an earthquake. I think they totally shut down on the Japan one, even for a sizable, like a 7 or an 8 or something like that, which is fairly common. They go in and they have to shut down operations. It's such a big signal, it swamps everything. They have to completely reset their system, I think, because everything's so balanced now. I try to say, don't spend all your energy trying to prevent, they're suppressing those signals, study them, learn them, find out everything you can about the Earth-based and solar system-based signals, which are huge compared to the stuff they're trying to read. I says, just do that, and then look, and then help people on Earth to do so. Sorry, that's my private. I will drum I want to beat. Say, come on, guys, get up to speed here. All right, so we got these isotopes, atomic. Okay, so all this. I haven't gone through everything. I try to. I'm sort of in the thing. Elemental data index, create atomic properties thing. More PDF. Don't do that, people. Just do the world a favor and put it in database. The simplest, cheapest, fastest way for the whole everybody. People get 4.8 billion people with browsers. They have JavaScript. They don't have anything else for the most part. If you're going to put something out there and you want to reach the most people, you put it out in a tab separated thing, because a one-line program in JavaScript can split that and get it immediately where you can begin using it. If you have to write a comma parser, and I've written them many times, they're horrible. You can spend weeks. It basically never can get closed because somebody always wants to stick in another thing, and this got quotes in it or commas in it now. So it's just an infinite recursion on there, and it causes infinite trouble. So just separate control characters, separate packaged characters, and then that's easy. So I don't know. I sometimes I get really tired and sad about these, people doing those that don't use PDF, because people, if you have, we have 2 billion kids, you can't make them all read and memorize this stuff. Okay, it's not good for them. So weigh anything that you do against 2 billion people, and they're young kids. They're the future, right? So physical constants, that's going back to here. These pages and pages of text and links might be good, when you were starting out on the internet years ago, but you can do this much more concisely. I can take this whole of NIST data and can get it down to one screen, okay? And you bring the stuff to the screen. You don't make the people go look for stuff. I found some really wonderful stuff on here. I will try to go through this again, but NIST is just one, okay? Now, you say, oh, well, there's only a few of the big ones, France and Germany and England and China and Japan and I don't know who else, rates in there, and say, well, we're the big central reference database. I'm being a little bit mean here. I'm doing it deliberately, okay? The countries, I worked in international development for almost a decade. I helped do long-range plans for every country. Okay, the Futures Group was there doing that, and I was asked to review what they were doing, so I was checking there, and I do that kind of thing by doing it myself as better than what they're doing. So anyway, so there's a lot of this in there, and there's a lot of money going out there, and there's huge needs, and the people are so smart, some of them, so capable, so much potential, and not always having the resources. Same thing's true of a lot of states in the United States, and poor schools, and poor states, and poor cities, So I've had that in mind in the 23 years I've been looking at the internet. I say, is there any way to meet some of the goals of global climate change and the environment and species protection and all of the things that are there. I keep a list of thousands of things that people think are good, everybody ought to do. And then things like this, physical reference data. Okay, now that's not actually a very good term. Okay, it doesn't capture all of what's going on there. And it's in English. Okay, so physical reference, 37,000. Okay, so standard reference data. So NIST is doing that. There. So these community, if I do a search like this and I get 37,300, I immediately think of this as a community. Okay, in a sense, when I say physical reference data, what I'm saying is this is a global community, or it ought to be. Okay, and my guess is that most of the people out there aren't continuously working together. Okay, occasionally people they'll meet human to human. If COVID allows them anymore, I don't know. They'll write on paper, and only people who have very specialized background, memorized all the magic words, can read it. Okay, so there's a lot of, I look at diffusion of data and information, MEMS and things on the internet every day. Every day, it's a fundamental part of understanding the whole. And pretty much, I see, things. You put it in PDF, it's like pouring water on a tiny flame. Okay, if you've got some really good ideas and things, and they get shoved into PDF, it's a kiss of death. You might as well. It's almost a waste. I don't throw anything away. But the effort then to take it and somebody writes a really wonderful dissertation, gets shoved into a PDF, nobody ever reads it. And yet if you go back there, I don't know how many thousands of them I've read, and how many that I followed up, hundreds of them I checked, what happened to those people? Where did they go? What happened? And they say, well, I gave that up. Okay, I did all that work, and it was really good. It could have really made groundbreaking. I could have worked in a community, and there's all kinds of other people I found. I just didn't have any way to work with them, that sort of thing. Because you can, everybody in the world who wants to measure the speed of light, everybody in the world who wants to measure the speed of gravity, everybody in the world. And I'm talking about when I was in grade school, I learned spectroscopy. It transformed my life. I said, shoot, I want to go do that, So, and I was building, studying neural nets in high school. I wanted to talk to everybody in the world. I could read the papers even then. I couldn't do what I can do now, but if I could go back and teach myself, I'd say, here, this is what you have to do to get through these things in minutes, not days, okay? So anyway, let me stop here. I'm trying to teach myself. I need to write all this down. I spent 20 years researching. Okay, I talked to people. I did a bunch of experiments. I worked with some large groups on the internet. I did a lot of searches, and spidering and crawling and studying, performance and methods and everything else on the internet, communities, all the different things. And then basically I said, I'm going to get too old. I better start talking to people and sharing this. So for the last 3 years, I've been trying to reach out to groups. So NIST, you're one, in a sense, one of my guinea pigs here. I'm trying to say, can I get you to change in some way? Can I help you, show you how to find your communities that you can connect to, the ones that really need things. Now, people, I was just looking at energy.gov, and they were saying, oh, well, we helped a couple of 100,000 kids, or maybe, I don't know, it was in the hundreds of thousands. And I said, well, you could go out and help 1 billion kids. Well, you can easily 100 million. Okay, you could do 100 million kids with a relatively low cost by just simply, putting things on your site, cooperating with the other people doing it. All the big guys I talked to the supercomputing groups, the exascale, and some of those last week. And I said, doing the same thing. I said, you have basically the potential to talk to every person on the planet. You have computers, literally, that can handle, conversations with with 7.8 billion people. Well, the 4.8 billion that are on the internet. So you could, and among the things you can do is have all of the global knowledge that's out there in forms where it connects together, where it goes into models and math, and the associated data for verification. You can have a store of stuff that makes sense, not like Wikipedia, however many millions of pages of stuff, not consolidated, not linked, not standardized, not workable. You go to Fourier transform on 35,000, I think now, on Wikipedia. There's not a single place you can actually use it. You say, show me how it works. Well, that means plug in my data or show me some samples and things in real time. How many students in the world are going to get exposed to Fourier transform? Probably 500,000. Probably easily 500,000 out there, maybe more. Okay, and and at any given year. So where did they go? Well, they can all go to their books and read it off of paper. They can go to a PDF online and read it off of there. They can go to Wikipedia and they can read paper stuff there, words. They're reading, eyeball to brain, try to make an association. It takes time to resolve. Then you have to go program the thing yourself. I said, no, don't make people start by trying to, recreate or extend, what they hadn't even learned yet. Let them use it, learn what it's for, apply it to real world problems, and then gradually, if they have a mind and it's needed, go out there. If you took all the stuff that's known about Fourier transform, then most of the people out there who know the word and use it even every day don't know all the wonderful things that are possible with it. When you go read the mathematics behind it, when you look at the physical applications of it, it's way beyond what people are using. And because it's not integrated in there, you have to go install this software, read these 50 papers, go through my website. Oh, it's broken. Too bad. So the form of the internet is kind of getting in everybody's way. The PDF is the worst. HTML is right behind. Wikipedia is right up front as one of the worst sort of things there. It's good if you're working with people who are trying to read things. Okay, if you're going to assume everybody's going to read and memorize this stuff. But if you want living models and you want this stuff to come together into larger pieces to solve real global problems, you have to put it all together. You can't just go say, well, let's do a little bit here, and in 10 years we'll have a conference, and in 50 years maybe we'll make some progress. Because the world doesn't have that time anymore. I'm pretty sure the world does not have that time anymore. If COVID happened and killed that many people, who were about 2.5 million a year, the U.S. says, oh, we're getting over it, and then that's only 332 million people, and there are many times that more in the world, and they don't have the resources and they don't have the vaccine. So what's going to happen? A lot more people will continue to die, and enough new ones will come in that they'll be out there and they'll get exposed and die later. The very youngest people are affected. It's the same as pneumonia or any respiratory disease. They're very old, and in fact, the curves are identical. I checked that. So, okay, well, I can see I'm trying to cram everything into this. So let me stop. Formula, those are fun. There's a lot going on. I looked at the protein folding groups. They're getting better, okay, and the protein structure and viral structures they can use the electron microscope group and the synchrotron radiation groups. Those guys, they can basically take really, really good pictures of these things. And there are groups now, there are enough groups that are come together, they can solve these things pretty well. They're getting better. And that's not getting disseminated out into the world. There's a lot of that could be used for other things. And someone did a molecular, let's see, what was it? Oh, molecular, I'll do it another time. Okay. Basically, instead of using an atom, which has only one signal in it, they took a molecule, which has many signals, and so it's extremely precise. You get what I'm saying? If you have one number, okay, and you do it, and you say, well, look, what can I learn from that? How precise can I be? Well, you're limited because you're holding on to one thing. But if you grab the whole of them, it has to. When people talk about the standard model, what they should be saying is, I have a certain number of constants in a mesh of relationships where I can calculate and solve the whole. Okay, and it can be done, but it needs to be open, auditable, clear. Everything hoverable and in infinite depth. So if you come in and say, if I hovered Planck mass, I should be able to get a hover on it as far deep as you want. Planck temperature shows up on the internet tens of thousands of times, okay? And those groups are not working together. They talk about stuff, they use some of the same words, but in their moments when they think about Planck temperature, if they had an idea, could go to the central group, contribute the new idea to it, stick it in there, and then it's never forgotten. And it's always there, in a sense, by its importance. If it's on paper, then humans have to go in and find those connections. If the computer's doing it, it never forgets. And it never forgets to check constantly. So that's the way I'd like it. Now, it takes a supercomputer to do it. Okay, we're not talking trivial amounts of processing there, but it's worth it. If you spread it out among all the computers on the internet, I know how to build things like that. That's kind of what I was doing. Nobody's helping me. I don't have any money. I can't pay people to go do these things. So I say, if you move in this direction, the pieces will start connecting, and then you'll begin to see that it works. So let me stop here. Thanks for listening. If you have comments, suggestions, ideas, that's what there's comments down below on the video, and I do check them. I don't get so many. In fact, I hardly get any comments. Maybe I talk about things that are a little too specialized, but they have global consequences for the most part. Okay. I'd like to know what, I'm looking at Planck's constant out of the corner of my eye. I'd like to know exactly what that is. I have a inkling of where it is. I've seen some of the possible other sort of physical models of where you could take that and say, well, what if it was a particle stream? What if it were a vortex? What if it were a Markov process? It could be a mathematical construct. It could be a physical picture or model that has mathematical versions where you can look at the consequences of. Then we could make some predictions and say, oh, okay, well, in this case, where the gravity is extraordinarily high, then the effective Planck, constant will change, okay? And it's easier to do that than to adjust everything else. You get what I'm saying? Is that everything moves in a smooth way if you change that, and then you have to make hundreds of other little dinky adjustments in different directions if you try to keep it constant. So I've been playing some of those games. I say, can we, particularly on gravity, the gravitational constant is not constant across the world. And I'm pretty sure the big G experiments have been having trouble for years, and I think I have a rough idea why that. What I have more is an approach where let's get all the stuff that we do know. When we do experiments, make sure you record sufficient data that you can track down what's going on. The gravitational potential is changing. The rate of flow of the gravitational potential at a given point. I treat it as a fluid because of it's easier. Okay, so the rate of change there, the gradients, the acceleration is changing constantly, and that is extremely precise. Those 3-axis gravimeters, every axis tracks it exactly, and it's just yours there. Anyway, but I haven't checked it at high frequencies. Now, every frequency for gravity is every frequency for electromagnetism is also accessible for gravity. If you want to build a terahertz gravitational detector, I can show you how to build it. You just plug in the numbers and go find the equipment, and if you can afford it, you build it. Okay, so it. Can you do a better job? Are there a lot of competing possible ways to do it? Yeah, because the detectors aren't tied down. Part of to do those kinds of problems is why I've had to work so hard on these other ones. Okay? You can't, if every single thing on gravity is down in nanovolts. Everything is nano. Just to get started, and to do the precision work like track trucks or ocean waves or earthquakes, you need pico. Okay, pico meters per second squared. You're down in there. If you want to track Venus, actually I found a shortcut for that. I think I can do that with our current detectors. Actually, I can track the moon with our current detectors. I'm talking about, is it there or not? Can I image the interior of it? I think I can do that. But, sorry, I shouldn't keep going, but there's so many things that need doing. And I'm down here just trying to get, the masses there. Because if we get all the data for atomic energy. When I say atomic, I mean from 10 electron volts per bond to roughly 1 MeV per bond, and that's the energies you need. So if you have a fuel with 10 electron volts per bond, it works out to so many joules per mole, right? Okay. And if you can increase that to say 100 electron volts per bond by using some of these interior states, these beta decay storage there, which I'm pretty sure I know how to do. Okay, I'm pretty sure that's a relatively straightforward thing with the skills that we've got in the world now. That we've got some wonderful groups out there. They're not working together, but they could do it. Now, if you get to 1,000 electron volts per bond, then you've got a good energy storage device, and you got fuels that are 100 times more energy dense than the fuels we have. So I take the 300-foot tall stack of fuel for a rocket now, and I chop it down by 100, and so I got a 3-foot tall tank now at a factor of 100. And I'm pretty sure the whole range in there is accessible. Everything up to about 1 MeV. All of those beta decay, all those weak interaction things. They're not weak. They're extraordinarily powerful. They're used weakly. Okay, you got wimpy uses of it, and it needs to be. Let's use it to lift rockets, into space, or to send them around the solar system faster. That sort of thing. Well, that's my agenda. My that's what I do all the time. Let me stop here. Thanks for listening.